Hello and welcome back to Geometry, Chapter 4, Section 4, Congruence and Transformations. A congruent figure has the same size and same shape, so these two would be congruent. If I rotate this one, these two are still congruent. Now, this might be confusing because it's a different way up, but all I did was rotate it. So I haven't changed any angles, I haven't changed the size at all. So all of these shapes are congruent. That means there's a rigid motion. I rotated it, I did a transformation, there's just a straight transformation, this is a rotation and a transformation. We could call this one a glide reflection. Not congruent would be if I had this shape and then resize that. These two are not congruent. These are also not congruent. So either different size or different shape. This one's also not congruent with those different angles. Alright, so congruent only if there's a rigid motion. So let's look at which one of these are congruent figures and explain. So Hij, looking through these, this shape down here looks like it. How is that one? We have USTU, so these two. And this could be a rotation about the origin. So we could say that's a rotation about the origin. Or you could also reflect it twice. We could reflect it in the x-axis and reflect it in the y-axis. So a couple ways that you could do this. EFG, this triangle appears to be congruent to this one. 3 and 2 in a right angle, 3 and 2 in a right angle, and it's reflected in the x-axis. So KLM, these two. That's a reflection in the x-axis. And then ABCD, this could be a glide reflection or a translation. Okay, so we could explain this as a couple different ways. We could call it a translation, so where we've just moved it from here to there, but because this has symmetry, it could also have been reflected or it could have been rotated. So we could also call that a glide reflection, either one or the other. Alright, a congruence transformation, that's another name for a rigid motion or a combination of rigid motions. So, for example, between these two shapes, okay, they're congruent, means there were a couple of transformations. Now notice here, this shape right here is 1 away, and this one's 1 away there. This is 2 away, and that's 2 away from the y-axis, respectively. Right? So if we reflect this in the y-axis, so a reflection in the y-axis gives us a reflection across the y-axis, would give us this shape, A prime, B prime, D prime, and C prime, and then a translation 4 units down. Would give us the new shape. So, 2 rigid motions. All right, theorem 4, 2 reflections in parallel lines. If you reflect a shape across 2 parallel lines, you basically get a translation. A reflection in parallel lines is a translation. Where the distance from your original point to a prime prime to your last point is twice the distance between the lines. So this line right here plus this one is the same as D. So from A to A prime prime is 2 times D, the distance between the parallel lines. Okay, and also this line from your first point to your last point is perpendicular to the 2 parallel lines. All right, here's an example question. In the diagram, we've got a reflection in line K that maps GH to G prime H prime, and a reflection in line M that maps G prime H prime to G prime prime to H prime prime. And we know that HB, this distance here, is 9. HB is 9. DH is 4. DH prime prime. This is 4. Alright, name segments that are congruent to each segment, to GH. Well, congruent to GH is GH prime, G prime H prime, and also congruent to GH is G prime prime H prime prime, because these are rigid transformations. Reflection is a rigid transformation, so those are congruent to HB. Congruent to HB, that's this line right here, is H prime B. H prime B or BH prime. And then congruent to GA, to this line, is G prime A. Does AC equal BD? AC, so from A to C equal B to D. Yes. Yes. Because perpendicular lines. Perpendicular to parallel lines. They're each perpendicular to a line, so they are parallel, so the distance is the same between them. Alright, what is the length G to G prime prime? G to G prime prime. Okay, we know that this is 9 and this is 4. We know that this plus this, 9 plus 4 plus A to C, B to D, let's call it A to C, is equal to 2 times A to C. Alright, subtract AC minus AC. We get 9 plus 4 is equal to AC. So, and we know that this is equal to 2 times AC from G to GG. So that is 9 plus 4 gives us 13. 2 times 13 gives us 26 units. Alright, reflections in intersecting lines. When you reflect something in 2 intersecting lines, it's like a rotation about the point P where those lines intersect. So from here, remember this is always a perpendicular line. the reflection, that's a perpendicular line right there. And then we have another perpendicular line here. Two reflections is like a rotation from our first point to the third one, where that angle of rotation from our first point to the last point is 2 times this one in the middle, 2 times the acute angle between the two lines. Well, we're not quite there. So, reflection in 2 lines is like a rotation about the point where the lines intersect, and the angle of rotation is twice the amount of the acute or right angle of the intersecting lines. Alright, so in this diagram, the figure is reflected in line K, and then reflected in line M. Describe a single transformation that maps F to F prime. So F, or the fish, mapped to F prime. So we've got a reflection here, right angle, and then a reflection here, right angle, or we've got a rotation that is 2 times, the rotation is 2 times 70 degrees. So a rotation of 140 degrees. And that's all for today, folks. Good times.